Hi folks, it's Alan here. If you've been following me, you know I've been spending quite a bit of time recently working on power supplies for the various pieces of equipment that I've been building. And there's a couple of examples here. The stuff on the left is the prototype of a 6-channel multi-output, highly configurable, very low noise power supply. The one on the right is one of my standard power supplies that I use for quite a lot of my equipment actually. That particular one is 5 volts at 1 amp ultra low noise, but there's lots of different things that need to be done. So I wanted to spend a bit of time today talking about what's actually important in a power supply. And to be clear here, I'm talking about power supplies for sensitive electronics. This includes both digital and analog electronics, but I'm not talking about power supplies for power amplifiers and high current pieces of electronics. That's actually a slightly different problem, which I will talk about again in a later video, but these supplies are specifically designed to solve a couple of problems. Now, one of the standard things is that virtually every power supply for digital equipment and for low noise analog equipment, such as phono stages or outputs from DACs and things like that, all of that equipment needs an extremely well regulated, very quiet, very low noise DC output. And there's a few requirements of that. It needs to be low noise. It needs to have absolutely zero ripple if you can avoid it. So you definitely don't want any mains breaking through onto the output of the power supply. And there's a lot of other requirements as well. But, you know, a lot of people think surely this is a solved problem. Now, switch mode power supplies aren't widely regarded because they do tend to generate quite a lot of electromagnetic interference and chopper noise because of the fact that they work by taking a DC voltage and chopping it at very high frequencies. So there's obviously a general preference for linear power supplies. So, okay, great, linear power supplies, here's one of mine. So what's a linear power supply built up out of? Surely, virtually any linear power supply will perform the same. Right, well, this is where we need to really start getting into things a little bit, because there are massive differences between what can be happening inside different linear power supplies that actually have a substantial result on the output. So let's talk a little bit about some of the kind of classic circuit technologies that were used for these things. So this is one that I'd like to talk about first, which is a pretty well-known type of power supply. It's an LM317. So this particular chip is widely used in an awful lot of different power supplies and quite a lot of equipment from a few years ago. But it's not without its drawbacks. Actually, the specification compared to modern standards is not that great, but there are nevertheless a couple of things that you want to look at in the spec, and I've highlighted those in green down at the bottom. And apologies for the flickering; I seem to be getting a bit of image problems there. So the first thing is that you need to look at is the output noise, and you can see here this is 0.003% of the output voltage, and I have to say that's not particularly brilliant by modern standards. But even worse than that, if you look here, that's only specified between 10 Hz and 10 kHz at 25 degrees C. So actually the noise at higher levels, at higher voltages and at higher frequencies could actually be quite bad, and actually in many cases it is really quite bad. There's the second thing that you want to look at though, which is the power supply, the supply voltage rejection, sometimes called the power supply rejection ratio. And here, if I'm using a 10 microfarad capacitor in the feedback loop, which I tend to, then this gives you here around 80 decibels of power supply rejection, which, you know, seems reasonably good. But again, look at this figure here. It's at 120 hertz, which is the mains frequency, plus, well, it's US mains frequency by the time it's rectified. But actually, that's not particularly great at looking at other higher frequency harmonics that may be breaking through onto the power supply. So the immediate thought is, okay, right, why not switch to some slightly more modern electronic components? And I have to say, yeah, there are plenty available. These are some of my favourites, actually, Analog Devices LT3045s, and some of the specs on these are immediately an awful lot better. So you can see here, the RMS noise is 0.8 microvolts per RMS, and that's between 10 hertz and all the way up to 100 kilohertz. So that's actually pretty good. And the kind of the ultra low spot noise at 2 nanovolts is also pretty good. That's an order of magnitude better than the stuff we were just looking at. The power supply rejection ratio, you initially look at and go, what? That's only 76 decibels. The LM317 was 80 decibels. Yeah, this is where the frequency matters. You can see this is specified as 76 decibels at 1 megahertz. If you look at this graph in the bottom corner down here, at 1 megahertz is all the way over here. That's basically about at its lowest point before you start getting into really ridiculously high frequencies. If you did this at exactly the same frequency that the LM317 was spec'd at, which is 120 hertz, it's up here. It's 110, 115 decibels of power supply rejection ratio. So clearly, it's already a much better device for producing very well regulated ultra low noise power supplies. But it has a few problems, which I can come on to a little bit later. And actually, if you dig into the details in the datasheet, these problems start to get reasonably serious. And I think probably the easiest way for me to talk about this is to show you how I've designed one of my power supplies and why. So let's move these out of the way and show you the innards of one of these things. And it looks a lot like this. Now, there are several stages in this that it's worth looking at. First of all, obviously, I've disconnected the transformer here for ease of moving around because the transformer is quite large and quite heavy. But basically, essentially, the output from the transformer, which normally sits in this hole, goes through a bridge rectifier here and then goes into a couple of large smoothing capacitors. In this case, I'm using a couple of Rubicon 10,000 microfarad CAN capacitors, which are clipping capacitors, and they're pretty good. And actually, what I'm then doing is I go into here a pre-regulator. So what I do is I take that rectified DC and I pass it through a regulator, and that regulator will then give me a fairly stable DC output voltage. In this case, because it's a 5-volt power supply, I'm actually outputting about 6 volts from that particular regulator. But that regulator, being a 3-terminal regulator, yeah, it's high power, it can get rid of an awful lot of the heat, it can get rid of the majority of the ripple that we're talking about coming in from the mains. But the output of that, as we saw on the previous kind of LM317, this isn't an LM317 by the way, it's an LT1085, but it still suffers from some of the same problems as the LM317. The output is good, but not brilliant. Great, so what do I do about that? The output is actually still reasonably high noise, potentially, and although it's fairly low ripple at the kind of AC mains frequency, it can actually have significant amounts of higher frequency ripple coming through if you've got harmonics on the mains and things like that. Now, I try to get rid of some of the harmonics on the mains and other things with a mains incoming filter here, but again, that's only partially successful. So I'll talk a little bit more about that in a minute as well. Right, so how do I deal with this? Well, first thing I do, I've now got a vaguely flat DC voltage, but it's not brilliant, and it may contain some high frequency components. So the next thing I do is, importantly, pass it through these two components. This one here is an inductor, and essentially what this does, the inductance, the impedance of the inductor increases with increasing frequency. So at DC, it's basically got very little resistance. It's a few parts of an ohm resistance. But actually at very high frequency AC, it starts to have a really significant impedance, which means that between that filter and actually some capacitors that are lurking down here below this bridge rectifier, I'm effectively forming a low pass filter. So only the DC that I'm trying to generate with this particular regulator is actually getting through. Great, so I've got DC and I've filtered out some noise. Right, there's still another problem though. High frequency noise, such as that produced by electronic equipment with large amounts of switching. This includes switch mode power supplies, televisions, fridge freezers, microwaves, computers are particularly bad. All of that actually will make its way pretty much straight through the mains filter, straight through the smoothing capacitors here, and actually even through the regulator. The regulators, as you saw earlier, these particular type are really not good at filtering out high frequency ripple. So I get quite a bit of high frequency ripple here, which this LC filter, this inductor capacitor filter here, gets rid of a lot of, but there's still a problem with that. Now, if you think about the inductor here, it's a wound inductor, and you get two effects in here. You get the inductive effect caused by it being a copper coil of wire that's wrapped around this ferrite core, but you also get a capacitive effect. Because the windings of this coil are right next to each other, you will actually get a small amount of capacitive coupling of the noise from one winding to the next winding to the next winding to the next winding, which means that very high frequency noise, such as that produced by computers at the gigahertz range, can just bypass that inductor almost entirely. So, oh, great, what was the point of doing that then? Well, it still gets rid of the low and medium frequency noise, but not the very high frequency stuff, and for that I use one of these things here, which is a ferrite. It's actually a ferrite bead with a wire passing through the middle of it, and these are excellent at getting rid of exactly the type of noise that this inductor won't get rid of. So by the time I come out of this inductor and the ferrite there, the electromagnetic interference, the high frequency noise that was originally present on, or might have originally been present on the mains, is no longer there. But it still has a problem. Okay, great. So I've now got a completely flat DC supply. Great, that's really good noise, really good news. No high frequency AC components are getting through. No mid frequency AC components are getting through. It's pretty flat, it's pretty DC. The problem is that it's still very high impedance. The output impedance after this stage, again, particularly at high end of audio frequencies in the kind of tens of kilohertz range, is actually quite high, and that's also not something you want. You want this power supply to be able to deliver current as and when the device that it's powering actually receives it. So in order to get rid of this, I need to do several more things. First thing I do is pass it through more capacitors. That basically gives me a bit of buffer, a bit of power storage, so that I can basically dump current into the final load when I need it. But then importantly, on the back here, I've got a bank of LT3045 regulators. So these are extremely low noise regulators. By the way, you have to do that filtering before these anyway, because again, if you look at the datasheet of these, they're great at filtering everything out up to about a few tens of megahertz, but actually beyond that they're pretty useless. Any high frequencies beyond about 10 megahertz just go straight through the regulator, and they specify that exactly in the datasheet. So these, however, these kind of take the output of that, all of that filtering and all of that noise that I've created, and then basically re-regulate it again, which gives me a perfect, very low impedance, very low noise output. Brilliant, I'm nearly there now. There's still some more to be done. Okay, first question is, why are there 5 of them? Well, unfortunately, these things here will actually only cope with half an amp each, so in order to get to the 2.5 amp spec of this particular power supply, I've had to parallel up 5 of them. Secondly, they're not very good at dealing with heat, so that's why I've only got a voltage drop of around 1 volt across each of these. So each one of these, even at maximum current, is only actually delivering about a couple of watts of power. So basically they can just about handle that. They get fairly warm, but they're well within their specified ratings. And most of the rest of the heat in this, the heat that's coming from the rest of the power supply, which is a much higher voltage originally on the DC in order to supply all of this, is being dumped via this regulator straight into the casework. So I've got good thermal management there as well. Right, very nearly there now. So I've now got a low impedance, very low noise, perfectly regulated output from this particular power supply. Only 2 things left to do now. The first one of those is I need to get that output to my equipment. And actually the typical way of doing that would be to use something like a standard 5.5mm to 2.1mm DC jack cable. That's great, but any noise then that's actually, if that cable then routes past some other equipment such as noisy mains cables or some more electrical equipment that has interference in it, the cable can then pick up some noise as well. So obviously you want to use a screened cable, and that's why I switched to these things. This is a standard aerospace connector with 2 pins, one for positive voltage, one for 0 volts, and also, importantly, a case. And the screen, this case here is screened and actually connected to earth. So any noise that's picked up on the earth screen is just dumped straight to ground and doesn't affect the voltages. And very importantly, 0 volts and the positive voltage, 5 volts in this case, both of those 2 voltages are not connected to earth. That's important. If the 0 volts was connected to the screen, then basically any noise that screen picks up is just injected into the kit that you're trying to power via the 0 volt line. Not really what you want. Almost there now. So the final part of this is a transformer. And actually the transformer, electrically, it's just giving me a decent output voltage. Great, okay, so there's lots of transformers on the market that can do that. So why do I pick these custom wound audio grade transformers? Well, 2 reasons. First of all, it means I can specify exactly what I want and get it in a nice neat little package which I can actually fit inside these cases, which is non-trivial. But secondly, these have also been designed to be low mechanical noise. And they do that in a couple of ways. The first thing is I use an over-specified toroid, an over-specified iron core to this, which is considerably larger than it needs to be for the power that I'm outputting. And secondly, that toroid is then submerged inside varnish, so it completely pots the entire innards of that toroidal core, and that basically prevents the iron from within there from vibrating. So this transformer is also almost 0 mechanical noise. Net effect, I've got something that's very low electrical noise, very low mechanical noise, very low output noise, won't pick up noise on the cabling between it and the device that you're trying to power. So this is, hopefully, at the end of the day, an excellent DC power supply. And actually the results speak for themselves. I'm using these with all sorts of high-end equipment now, and actually the results I'm getting of these power supplies are considerably better than even the ones that you're getting with very expensive audio-grade power supplies. And they're just knock other small linear power supplies into a cocked hat in terms of their output performance, and the audio performance you get from things that these are connected to is second to none. Hopefully that's helped to explain a little bit about my design philosophy behind some of these power supplies, and hopefully you understand a little bit more about why they are quite so complicated.